give the formal specification, the formal definition of this machine M, we can write out in detail how the transitions occur from these states of M. Now, the state of M is in fact an ordered pair, where the first member of the ordered pair is the state of machine M1, and the second member of the ordered pair is the state of machine M2. At a given moment, reading in the input stream. Okay. Now, so that's like a core idea. So, how many states then will this machine M need? Well, if machine 1 has K1 states, and machine 2 has K2 states, then the possible number of ordered pairs of the states of M1 and M2 will just be K1 times K2. Okay, so that will be that K1 times K2. That's the number of states, number of pairs, possible pairs that we will have in our machine M. Okay, so we've now decided, and you may ask, well, why? Why did you choose this approach rather than some other way? Well, usually it works, and it's quite ingenious. And when we come to the formal proof, things should click. You'll understand better, I think. So that decides on the states for our machine M, and so the transitions in machine M will be between these pair states, from one pair to another pair and so on. And how do you do that? Well, take a given pair and another pair. Well, no, take a given pair. And how do you generate the next state in machine M? In other words, how do you generate the next pair? Well, you find the next state of machine M1, and that will be the first member in your pair for the next state of machine M. And in the current state of machine M, have a look at the second pair, and remember that's the current state of machine M2. Okay, so find the next state for machine M2, and that will become the member of the pair for the next state in machine M. I hope you followed that, because that's the core idea of this whole proof, in my view. Okay, so if you didn't follow it, rewind. Okay, so your transitions are changing the current state, which is a pair of states of machine M1 and M2, into a pair of states, next states of machine M1 and M2. And those two pairs, the current state of machine M and the current state of machine, the future state, the next state of machine M. Okay, now when does this machine M accept? It will accept when either M1 accepts or M2 accepts. So that means that you have to be, machine M has to be in an accept state when either M1 is in an accept state or M2 is in an accept state. Right? That's another idea, and this will be clarified in the detailed proof. Okay, so you have an input stream. It's read effectively, in a manner of speaking, by simulation by both machines, M1 and M2, in parallel, in a manner of speaking. And when one of them, or if one of them accepts, then M will accept. Okay? Alright, so that's what we're just saying here. So if M1 and M2 is in an accept state, then M will accept. Right, now the actual detailed proof, well, start on it, and we'll need 1.5 squares almost to go through it. Right, so you're given two languages, regular languages A1 and A2, and you have to find a machine M it's a construction type proof, a proof by construction, right? So construct or design a machine M that recognizes the union of A1, language A1 and language A2. Both are regular languages. Okay, so let M1 recognize A1. Okay, and M1, here's its formal definition. It's 5-tuple. So its set of states Q1, the alphabet. Oh, by the way, we're assuming, keep things simple, that the alphabets, plural, of language A1 and A2 are the same. Okay. Now, I think do I mention it? I think somewhere a bit later, I mentioned a modification you can make to the proof if the languages A1 and A2 have different alphabets, like sigma 1, sigma 2. But in this proof, keep it simple. You notice here, like this is the 5-tuple, the formal definition of your second machine, M2, and the alphabet here and the alphabet here are the same. Okay, to simplify things a bit. Okay, so this is the formal description, your 5-tuple for machine M1. Here's your, what's the word? Transposition, sorry, transition function, okay, for machine F1, and transition function for machine 2. Okay, start state Q1 for machine 1. Let's say start state Q2 for the second machine, and F1, this is your set of accept states for machine 1. This is your set of accept states for machine 2. Okay, so you're given these two. So these two machines, they recognize regular languages. Okay. By definition, regular languages have automatons that recognize them. Okay. Now, the aim is to construct a machine M, different from M1 and M2, that recognizes the union of these two languages, M1 and M2. That's the union operator, union symbol. Okay. And now we can't draw a state diagram, state transition diagram, because certain parameters are not given a definite value. It's sort of indefinite, general. So the only choice we have is to write down a formal definition, a 5-tuple. Okay, so assume here's your 5-tuple for your machine M. Right now. So I've got a 5-tuple, so I will discuss 5 points, talking about how do you construct each of these, each member of the 5-tuple, and so talk about 2 of them in this session, and I don't know, maybe you can see this top line here. So the third one, that to me, in my view, was the heart of the proof, is specifying what the transition function is. You won't be able to see it, it's like on the third line. And the fourth member of the 5-tuple and the 5th as well. And then a bit of comment, and at the end of the next session we start talking about another proof. So that would be proof 1.26. But we don't get very far with it because we get stuck. There's a major problem, and that in turn leads to a discussion of a major topic, concept in theory of computation, and it's called non-determinism. So for three and a half squares, so nearly 2 sessions, we will start talking about this very important concept in computer science, computer theory, called non-determinism. So that will be a kind of digression, a large one, an important one, and then finally we'll come back and try to prove this next theorem, which is trying to show that the class of regular languages is closed under the operation of concatenation. Okay? But with the techniques we have so far with deterministic computation, and I'll explain what that means in a few sessions from now, can't do it. We can't prove it. We don't have enough tools. We don't have enough power. So we need this concept of non-determinism, and that what it is will become clear in the next few sessions. Very important concept. All right. So let's talk about Q, and that's the set of states for the machine M. Okay. Now we've already talked about it because it's a core idea, one of the basic ideas of the proof. We said that Q would be an ordered pair, and the first member would be the state of well, in this case it's just a set, right? So this first member is a member of Q1, and the second is a member of Q2, right? The set of states for machine M1, set of states for machine M2. Right? So this member here is in fact a member of the Cartesian product of Q1 and Q2. Okay? So this is just one member of this set, Cartesian product set, right? And the first member is a member of Q1, second member is from Q2. Okay. Now the second one, fairly simple. The alphabet, the two alphabets are just the same. Okay? We'll just specify the alphabet of machine M will be the same alphabet as these two, and these two are the same, and these are the same. So we've got three alphabets, all the same. Okay? So it's so the alphabet for machine M here, this one, is just the same as the same alphabet for A1 and A2. Now look, oh, here it was. So if this and this were different, like if that were sigma 1, that was sigma 2, and if they were not the same, then you could modify the proof a bit. It just makes things a bit more complicated. And then you would define sigma, that's the alphabet for machine M, as the union of the two alphabets. Right? And then that makes things a bit more complicated, but it can be done. But it's complicated enough already. So let's let's just work with the same alphabet right through. Keep things simple. And next session, I'll talk about the third member of the 5-tuple, the transition function delta, because that's the core of the proof in my view. Okay.